optimizing. We got a game plan. Remember, you can pause this and write this down. 1. The equation, you're going to find the equation you want to optimize. Then, you want to find a constraint. So, you can get the number 1 in terms of one variable. Then, you take the derivative and find the critical value. After that, you test the critical values. So here's the problem. We want to find the point on the line y is equal to 2x plus 3 that minimizes the distance to the origin. So if we're minimizing distance, step 1, find an equation to optimize. The distance formula. That's x2 minus x1 squared plus y2 minus y1 squared. Yeah. After that, we need to find the constraint, but they gave it to us. There it was, Robert. They gave it to us. Y is equal to 2x plus 3. And they gave you the origin, that point. So we're going to plug those into the distance formula. X is just himself, minus 0. But y, he's the imposter. He's 2x plus 3. Now we multiply that out, because it's going to be easier to take our derivative that way. And when we do, we get x squared plus 4x squared plus 12x plus 9. But let me remind you, 2x plus 3 squared, you use the binomial expansion. That's 2x plus 3 times 2x plus 3. Then we gather, collect, and combine. Gather, collect, and combine. We combine our like terms in x squared, and we get 5x squared plus 12x plus 9. Fine. So then now that we have our one variable function, we're going to take the derivative. We're taking the derivative of our one variable function, that d. Okay, so we go, and we use the chain rule. The chain rule. That's 1/2, the inside, to the minus 1/2 times the derivative of the inside. Then we'll clean that up to make it a little easier on the eye. And when we do, we get 5x plus 6 over that denominator. Wait a minute, where did the half go? 10x plus 12. Oh, those both have a deuce. So I pull out that deuce, and I drop those deuces. And that's how I got the 5x plus 6. To find the critical values, we set it equal to 0. But that fraction is only equal to 0 when the numerator is equal to 0. And you get critical values when the denominator is undefined. So we set the numerator equal to 0, and we solve for x, and we see that it's a curious minus 6/5. We can get our critical values of our denominator by setting it equal to 0. But it's only equal to 0 when the radicand is equal to 0. So you set that equal to 0 too. You try to factor, but to no avail. So you try the quadratic formula, but you get lazy. So you use the discriminant, the stuff underneath the root. B squared minus 4ac. If it's negative, that has no solutions. Aha! It doesn't have any solutions. So that doesn't have any real zeros, and that's going to help you when you're testing your interval. That has no real solution. So let's go put our critical value on a number line. Our critical value was x is equal to minus 6/5. And what are we checking it in? We're checking it in the derivative, because we want to see where the derivative changes signs. So we put it on a number line. So we test the number to the left of minus 6/5. Like minus 1,000,000. When I put minus 1,000,000 in there, the numerator is negative. The denominator is never going to be negative, because it doesn't have any real roots. So, boom, we're negative in that quadrant, or in that region. Let's check it. Number to the right of 6/5. I see you have your future. We put 0 in that numerator, and we get it positive. That's why we're positive in that region. So we're going from negative to positive, meaning we have a minimum. And our minimum value is that x is equal to minus 6/5. So now that we got that x, we need to go get our y. And we get our y by putting that in the constraints. We put that sucker back in the constraints. That y is equal to 2x plus 3. Oh, there it goes. And y is 3/5. But what's my point? My point is, that's the point. Minus 6 fits, 3 fits. Let's see if this fits our idea. Take a look at the picture. There's our line, there's 3 fits, and it does look like that's the minimum distance.